Welcome everyone. My name is Sylvain Lézé from the Department of Aeronautics at Imperial College, and this is the new episode of the UK podcast Turbulence at the Exascale. So if you're not familiar with the podcast, we are trying here to gather the view of the community in the UK regarding exascale computing and what are the challenges and opportunity for the turbulence community if we want to harness the power of exascale computing. So the podcast is one of the initiatives of the ExCALIBUR project, which is the UK answer for the transition to exascale. It is led by the Met Office, the UK Atomic Energy Authority, and the UK Research and Innovation. And its aim is to deliver research and innovative algorithm development to harness the power of exascale computing. So I'm the lead of the ExCALIBUR working group on turbulence, and I'm also leading the UK Turbulence Consortium. So this is where this podcast is coming from. And today I'm very pleased to say that my guest is Pablo Ouro, who is Dame Kathleen All-Earnshaw Fellow, I hope I said it well, at the University of Manchester. And the reason why Pablo is with us today is because he's an expert in high performance computing, computational fluid dynamics, and renewable energy. And he has also some experience in software development. So it's going to be very interesting to hear about his experience, his research, and his view on exascale computing. So good morning, Pablo.
Good morning, Sylvain.
I'm very happy to have you around, and we are going to crack on with the question. And for those who don't know you very well, can you tell us more about where you are from, what you have studied so far, and how did you end up with this fellowship in Manchester? Oh,
well, I would.
Yeah, go on. Sorry.
So I would just thank you for the invitation, and I will introduce myself. So I've studied in Spain civil engineering from the background in Coruña, which is the northwest sort of wet part of Spain. It's not the sunny south, but it's a great city and a great university. And once I was doing my MEng, I studied also in Chalmers in Sweden for a year during my Erasmus, because I was starting to feel interested in CFD. And they have a very good reputation. So I also went there for a year to learn from the best. And then in 2013, I decided that I wanted to do a PhD abroad because the situation in Spain wasn't good. And then I also wanted to improve myself. And then I ended up in Cardiff doing my PhD, where I stayed for 7.5 years at the end of the day. So I did my PhD, and then I was research software engineer for supercomputing Wales for 18 months. And then I promoted to a lectureship in computational hydraulics at Cardiff Jet. And then since September last year, I joined the University of Manchester with a 5-year fellowship, as you well mentioned before.
Fantastic. So you joined Manchester just before the COVID-19 pandemic?
No, just after.
September 20. Okay. So yeah, okay. So you didn't have the opportunity to go on campus, or not that much?
Not yet. So I remember doing the interviews, I think it was March, and I was saying, things are not going to go that bad that I can't go to university. And here we are. Okay.
So I usually ask my guest, I guess for you it might be challenging to answer, but what are you enjoying so far working at Manchester University?
Well, to be honest with you, Manchester has always been an iconic place for computational fluid dynamics and fluid mechanics. Everyone who has been working on that or knows a little bit, Oswald Reynolds or Brian Launder. So it's always a place that you have in mind, like, okay, this is the place to go. So I decided to move to Manchester because the position is really good. The offer that I had, it was really good. And then because working with colleagues of such caliber is really motivating. So it's one of the best groups in the UK and in the world, I would say. So I have the opportunity to work in very big projects, some of them linked to the tidal stream energy community, working with researchers and industry. And they are also very attractive and and state-of-the-art developments in the CFD with some of the colleagues. So to me, it was a great opportunity. It's also very well ranked. So, I think it was a wise choice.
Great, thank you. And you said you started your studies around civil engineering, and I was wondering, how did you become interested in high performance computing and well, I will say in turbulent flows in general?
Well, my story with CFD is a story of love and hate, because when my civil engineering background didn't have any fluid mechanics, so that was a bit strange. But I was introduced to what it was my MSc thesis supervisor, who was doing CFD, and I said, okay, this sounds pretty good, and I saw the simulations you can do. And okay, why not? So that's why I went to Chalmers, and then I continued to do my MSc thesis that lasted 1.5 years in Spain. Those theses are pretty long. It's not like in the UK that we have 3 or 4 months. It's a huge one. So I started to be very interested, because even though it was hard at the beginning, you have to code, you have to understand the basics and process information and validate and whatnot. But then when I started my PhD at Cardiff, it was about large simulation, and I was doing shallow water modeling, which is more basic than LES. So the idea that Professor Stoser suggested was to develop the code so we can simulate tidal stream turbines, which was new back then. And the code was always meant to be for computational hydraulics. So we wanted to bring it to the next level of applicability. So everyone who is working on DNS, LES, know that if you want to run a proper simulation, you need a proper supercomputer. So I came from my desktop code to a massively parallel code that we needed to run efficiently. So at the beginning, when you start implementing things, you do it in a mathematical way, which is not always the best in terms of computation. So if I consider myself a bit perfectionist, I always wanted to run it faster and faster, because you can't, if you are waiting for 3 weeks for a simulation, it's way too long. So you want to make it 2 weeks or 1 week. So that's how I started to get familiar with MPI, to start implementation with OpenMP, and you can see the improvements you can do, and the overheads that one thing might have if you do it in a proper way or in a wrong way. So I like it. I like HPC because it's something that is rewarding at the end of the day. If you do it well and you can run very fast, you can get very good results from quite exciting simulations. So when you combine HPC, turbulent flows, and renewable energy, to me it was like perfect combination. And so far it has been proven to work pretty well. So that's looking really good.
Great. So a follow-up question. Well, you already touched on this, but so you are mainly using Hydro 3D, which is, I guess, the code you have been described. So can you tell us more about the story of Hydro 3D, about what type of numerical methods it is based on, and what's the current parallelization strategy?
Yep. So as I said, Hydro 3D has been developed for a number of years. I started with my former supervisor, Thorsten Stoser, and then it was mainly focused on computational hydraulics. So we have hydraulic and environmental flows to simulate rivers and turbulence, sediment transport. And the structure of the code is quite classic in terms of it uses a Cartesian grid with rectangular subdomains, so we can make the simulations as fast as possible. So we are using finite differences. We don't have connectivity between the elements, so it's very straightforward to parallelize what we have, which is MPI, to make it as fast as possible. That was probably the goal that we had, which is similar to most of the codes that have been used for DNS or LES or wall-bounded turbulence, right? You want to have a very, very high resolution near the wall, but then to make the simulation to run as fast as you can. So Hydro 3D is very classic in that sense. We have a fractional step method to resolve the simulation in time. We have staggered storage of velocities. So it's pretty standard in that sense. The latest development of it is basically coming from its advantage that I see from this code, which is its flexibility. It's a code that allows to include more and more functionalities and use them all together at the same time, which is something that you might not have in other kind of codes. So for instance, for the last 6-7 years, we have implemented the mesh boundary method to simulate the tidal turbines. More recently, all the techniques, what they call actuator line, actuator disk, to represent tidal turbines. With the goal to simulate offshore wind farms and tidal stream turbine arrays in an efficient way. So we have developed from a purely computational hydraulics Eulerian framework code to what we have now, which is a more functionality, diversity, let's say, code, which I would say it has evolved towards something that I called DOFAS, which is Digital Offshore Farm Simulator, which is basically a combination between the background, the CFD, either 3D solver, and all the functionalities in terms of turbine representation. And what is coming now, which is going to be thermal stability and all the kind of things we need to implement to simulate amongst very boundary layers, so we make a more versatile software.
Great, amazing. So I've seen that you've published recently a work about Hydro 3D and how does it perform on various CPUs. So are you team Intel, team AMD, or team ARM? What's the best processor on the market at the moment for Hydro 3D?
Well, you're putting me in a bad position. No, well, nowadays I would say I'm team AMD because it's the one providing us the best performance, way over Intel or ARM. So, well, the work is not yet published. We are actually doing the reviews at the moment, so hopefully it will be published in a month or so. And the story of it was that back in 2017-18, I was research software engineer for supercomputing Wales. So I was working very much on the improvement of the code. And I got in contact with Simon McIntosh, which you interviewed a few weeks ago, who got the new Isambard supercomputer funded by the GW4 universities, which are Bristol, Exeter, Cardiff, and Bath, to build the first supercomputer production stage supercomputer with ARM processors. So it was a very good opportunity to have the access to the first of its kind machine. It doesn't happen every day. So we were wondering, okay, how our code is good to perform on that, because we have seen some simulations done at Barcelona supercomputing a few years before, but the latest ARM processors, the Thunder X2, seem to be a new generation and seem to be very powerful. So we said, okay, let's see how it performs. So someone invited us to a hackathon in Bristol, and we were quite amazed because we were able to compile and run the code almost straight away after 2 or 3 hours of changing a few bits. So that was the first milestone, I would say, back then. And then we tried the code because, well, I should say that the advantage of the ARM processors is that it has more bandwidth capabilities. So we know that CFD codes are mostly memory bound instead of compute bound. So we were hoping that the ARM processors would enhance the performance of our code and other codes such as OpenFOAM and some other. So then we did the test, everything went pretty well. And then the next stage was to compare to the chips that we had in supercomputing Wales in the partition that we had at Cardiff, which are the Intel Skylake and AMD EPYC Rome, to see, okay, we have 3 state-of-the-art processors, which one is taking the lead here? So we did several benchmarks, classic benchmarks in the CFD community, and another one involving a solitary wave, which is more complex because you have to resolve the Navier-Stokes equations plus a level set method, which is already complex in itself. And then basically what we see is that the AMD processors, which has more memory channels than the Intel processors is providing us the best performance. But I would say sometimes it's one order of magnitude faster than Intel, which is quite amazing. And then when we compare the Intel, Skylake, and ARM processors, what we see is that they are fighting one another. So sometimes we got faster computing with the Intel because it has higher clock frequency, so it's able to digest and process the information faster. But then when we increase the resolution, when we have more degrees of freedom, let's say I think the highest we did it was 1 billion grid cells, then the ARM processor is taking over because it has more capacity to transfer the information through to the memory bandwidth and more memory channels. So this is bringing an interesting question for the current HPC community and exascale community. What is going to be the hardware that is going to provide the codes, the best performance in the future? So what we did, it was to evidence, if you take a code, you run it there, what is the performance you get?
Great, thank you very much. I think everyone is going to be looking at this this comparison and this paper, which hopefully will be published very soon.
Hopefully.
Do you have any plan to deal with GPUs for Hydro 3D, or you're going to stick to CPUs for the time being?
I don't think we are going to jump into pure GPU code. We are thinking about whether MPI GPU, a hybrid scheme, might be something attractive. So we can some of the subroutines we have in the code are likely to be parallelized on GPUs and then make the most out of them. But that is something that is not in the plan at the moment. So what I'm seeing, what I'm learning from colleagues at Manchester, such as Alistair Revel that you also interviewed, they are using GPUs to run the lattice Boltzmann codes on it, and it's looking, really, really fast. But it seems that the more you add onto the code in terms of the multi-physics, for example, then the overheads just kill the performance. So I think that there has to be a trade-off between the performance that you get from an MPI-based code, from a GPU-based code, that joined together can make the most out of them. So probably in the future, we might need to explore that to see how it works.
Okay. So I was about to ask you, well, it's a very similar question, I guess, is what do you think are the challenges associated with exascale computing to study turbulent flows? I'm asking because it's very likely that the exascale supercomputers are going to be based on a mix of CPU and accelerator technology, like GPUs of some sort. So how do you see the future for Hydro 3D? Do you think you will still be able somehow to use the next generation of supercomputers, or you will have to rethink the parallelization strategy?
Well, I definitely think that if the machine is available tomorrow, we can just compile and run the code. But I think the key question for me and for everyone in the HPC community is whether we can use the exascale resources efficiently, because we can all run in the machine and then get the results. But are we making the most out of it? Are we just taking too much time on the communications overhead? On the computations, we have to look for the balance, and because we don't have the machine here yet, we don't know actually how we are going to achieve that. Definitely exploring the hybrid MPI GPU stuff is something attractive, but I think we also have to be mindful of the necessities of the codes in terms of the chip architecture. As I was mentioning before, the research we've done with comparing the 3 different processors, it might prove that for my code, for instance, the AMD structure with more memory channels is providing us the best results, but it's possible that for some other, I don't know, but I mean, you have been within compact, which is through the spectral, and you rely on the FFTs, it might not be the case. So I see the exascale challenge quite broad in terms of the things that might go well for me, might not go so well for you or some others. So we just need to go and see and try and decide, okay, what's the best strategy to go forward.
Great.
And that's on the computing part. And then I agree with the podcast from the NREL colleagues that I watched it, very, very interesting. And they pinpointed the crucial bit, which is going to be the data processing. So nowadays we are generating, so I would say, mostly gigabytes, somehow terabytes of information. But when we move into the next scale, how much are we going to be generating? I think terabytes is going to be the minimum amount of data we'll have to post-process. And all now with the threat of machine learning and artificial intelligence and whatnot, then, for training and machine learning code, you need vast amounts of information. Are we going to the petabytes, and how we are going to deal with that? So I like the approach they took in supercomputing Wales, which is to have a proper cluster for computing on one side and a data analytics unit on the other side. So you can just run the simulation here, but when it comes to processing or machine learning, then you have a different unit. And I think that is an attractive way that we should explore in the future.
Okay, that's very interesting. One more question about exascale computing. If tomorrow you have access to a big exascale computers, what is it going to change for your research? What are you going to be able to do that you are currently not able to do, and what do you want to do that you cannot do at the moment?
Well, to me, exascale computer, what it's going to mean is that we can go beyond the physical domain we are currently dealing with. So in the developments we are doing for DOFAS at the moment is looking at offshore wind farms. So we are able to simulate a single offshore wind farm, which are domain, let's say 10 kilometers, 20 kilometers long and 2 meters high, something like that. And we might be using 2,000 or 3,000 processors to run efficiently. But if we have access to a scale computer, then it means that we can go beyond that. And one of the key things in my research fellow that I want to look at is to the interaction between offshore wind farms, which might be separated, I don't know, 100 kilometers away, or the interaction of offshore wind farm with land. I mean, we are this week, Vestas unveiled the latest offshore wind farm, which is going to have I think it's 236 meters diameter. We are talking about huge machines, and now what we have, I think, is in the London array, we have machines that are 150 meters diameter. So we are going to a bigger scale that these farms are going to have a larger influence on the atmospheric flow. And then an exascale computer, what it means is that we can actually resolve the flow at turbine scale, but also capture the turbulence and the wake of the whole farm in a wide range of spatial scales. I think that's what I see exascale computing providing us the new capabilities about.
Great. Now, so you have been spending quite some time in the UK now, like 7-8 years. And so not just talking about you, but talking about the CFD community in general in the UK. Do you think that the community is ready for the transition to exascale computing?
I think we are ready to test which computing framework or paradigm is going to perform best initially in the exascale machine. So in the UK, I think we are fortunate. Probably fortunate is not the best word because we have invested in that. So it's something that just comes out. But we have a breadth of codes out there. So we have SBLI, we have in Compact 3D, which all of them are different in the terms of how you resolve the physics. You have lattice Boltzmann now running on GPUs. So I think the question about whether we are ready or not, I think we are ready to try all these different pieces of software and see which is the one taking the most out of the advantages of an exascale computing. And probably we will see that the initial exascale machine is going to be very different to the second or third generation of machine, which those I need to learn from what we see in the first machine there. So I think we are ready to give the information to set up, to try the codes on the first machine to inform the second generation of exascale computers, which need to be more efficient.
Thank you very much. That's a very interesting point indeed. So, well, you said at the start that for your flow solver AMD processor so far seems to be working very nicely with more memory capability, which is great. But I wanted to ask you in terms of hardware, if you could change something in hardware, what would you change and why? Do you like more memory, more network, more higher frequency for the GPUs, CPUs? What would you like in an ideal world?
Well, I think I would go back to the point that I've done before, which is basically the needs for each of us might be different. But for us, because the way that we want to progress in terms of simulations in the next 2 to 5 years is looking at the multi-physics. We just don't want to resolve mass and momentum conservation, looking at velocity suppression. But we want to look beyond that with temperature, humidity, and even the actual implementation of the turbines in the flow domain is bringing more multi-physics into the problem at hand. So we are going to need to transfer a vast amount of information between nodes, and we need to do it efficiently. So I don't think computing is an issue, and the more people I speak about it with, they say, computing might not be an issue. I think what we will be facing in the CFD community when we go to multi-physics, multi-scale, is the transfer of memory between the nodes, and probably we will reach the network latency at some point. So what I would see is that probably memory channels and memory bandwidth becomes more relevant, again, in my field than clock frequency.
Great, thank you very much. And I have one last question. So we talked a lot about exascale computing, but what do you think will happen in 10, 15 years? Do you think we are going to have incremental changes? So GPU, CPU that are more powerful, more efficient with more memory, or do you think we are going to have a drastic change in terms of hardware? Basically, in 20 years, where will you be doing your simulation? What do you think on that?
Who knows? Right, I think I would make 2 points here. So if I look back, I think I consider myself to be relatively new to the field. I mean, 7 years in the making is not too much. There has been people doing this for many decades. But I look back sometimes at 2014, 2013, when at Cardiff University, we had a sort of small cluster, relatively small cluster with Intel Sandy Bridge. And we didn't have many cores. I think we have like 100, something like that. So I remember for us, it was really, really hard to run high resolution LES of a single tidal turbine. We were struggling, or it was taking lots of weeks to run. And then eventually we upgraded the machine into the supercomputing, HPC Wales and supercomputing Wales later on with the Intel Skylake and the AMD. And then we can see, okay, there is 1 order of magnitude improvement here. And that was really good. So I would expect that as well into the exascale machine. But it means that before you have very little resources, relatively little resources. So you need to really think how to make the most out of them, right? You write your code, it doesn't run very well. So you need to optimize the subroutines, the communication, the computation, and everything. So there was a lot of brain put into it. But now you will be driving a huge HPC machine, which is going to be able to do whatever you want. And I think, and I fear, people are going to take just not that efficient codes, not that efficient languages, not suitable for HPC, and just leave it to run there. And that might be an issue. We need to think that exascale computers, or the machines that are coming in the next 5, 10, 20 years are going to be super powerful, but we need to use them efficiently. And that brings into the conversation my second point, which is the energy consumption. Few months ago, I read some information about the power needed to drive an exascale machine, and that is going to be gigantic. It's going to be so much power we need to plug into there, that we really need to think that when we run a single simulation in, let's say, thousands of processors, it's going to consume X amount of energy. So I think what I would see in 20 years' time, myself running simulations, or my students, it will be in a machine that is powerful, but the chips are developed so the energy consumption is much more reduced. So just remember that when we were hearing about the ARM processors back in 2017, I mean, ARM chips come from the mobile phones, right? What you have in the iPhone, Samsung, whatever mobile phone you have. And the key bit of those chips is that they have a low energy consumption. Mm-hmm. And then we say, okay, great. When we wanted to test them, we wanted to know what was the energy consumption of those, because if you get a little bit less performance, but more reduction in the energy side, then that's great. But that wasn't the case. Actually, what we didn't see any decrease in the energy consumption, which was a bit of a bummer, because that would be huge. So 20 years time, I think energy is a variable that needs to bring into the HPC community, and we all need to be mindful of that and teach our students, okay, you need to run this, and we need to extract this kind of information, but we can't run that 20 times, because that's the whole energy consumption of a household. Things like that, we need to put it on the table eventually.
Well, thank you very much. Hopefully, in 20 years' time, supercomputers will be powered by wind turbines, right? So,
well, yeah. Hopefully, Archer 3 and is a wind farm and a huge machine.
Yes, why not? Thank you very much, Pablo, for your time and for your input. And well, we wish you all the best. Sorry for your fellowships. Hopefully, you will be able to do what you want in terms of research. Thank you very much all for listening to this new episode of the podcast. All the links are going to be put on Twitter. It's UK Turbulence, or you can also find the links and the playlist, YouTube and SoundCloud, on the UK Turbulence website. Once again, UK Turbulence in one word on Google, and you will find us. Thank you very much, Pablo, again for your time.
Thank you, Silvano.
And thank you, everyone, and see you soon for a new episode.